Can everyone hear me? Yeah. Firstly, I'd like to thank Alvin and Natasha for organizing TriSwift and everyone else who helped organize this conference. It's really great to have a Swift conference in India. I'm from Kolkata, so not much love for Swift there, but yeah. So I'll be talking about declarative programming in Swift. Um, let's get started. So a little about me before I start actually. I've been writing Swift since the day it was released. I've been writing aggressively generic frameworks for the past 2 years. I've been focusing on framework design. I'm really interested in compile time and runtime metaprogramming, and really nervous about this talk. Uh, so this is, I guess, where declarative stands. So there's imperative programming, and then there's object-oriented programming, there's declarative programming, and then there's functional programming, which is completely out of scope for this talk. But yeah. Okay, so this talk is going to be biased because Swift is not a pure declarative language. So what constitutes as declarative Swift is debatable and subject to interpretation. So yeah, Swift is not a pure declarative language. And yeah, so this is something I saw on Twitter a week ago when they released when they allowed 280 character tweets. Someone made this comparison between normal print and something completely blown out of proportion. And this is what I tweeted after a few days. So basically, yeah, the idea is just because you have more space doesn't mean you should, expand into that space. And this is actually a good example of what an imperative versus declarative scenario looks like. So the code above it uses a for in imperative loop, and I initialize a variable, and then I loop over 1 to 100, and then I add it to that variable, and then I print it. But in the second version, I don't have to do any of that. It's just a one-line thing. And I use reduce, which is a high-order function. It takes another function as a parameter, and I use the plus equal to operator. So it does the same thing. They both print 5050, which is okay. So yeah, this versus this, if you guys couldn't see before. So what is declarative programming? It's a program paradigm. It's a style of building the structure and elements of computer programs that expresses the logic of computation without describing its control flow. So this is the Wikipedia definition, but yeah, not Superman. So what it isn't, it's not a silver bullet. It's not a substitute for imperative programming, because Swift is not a pure declarative language. You still have to do some imperative programming, but it's not less code, and it's definitely not less code, because I'll get into it later. So the advantages of declarative programming. Zero cost mental parsing. Basically what you see is what you get, as in you write code that corresponds with your mental model of what it is. It's extremely modular because you separate the what from the how with a layer and direction, so you can easily swap out the implementation without changing the main declarative part of the program. It's you require less documentation because your code is self-documenting. Separates description from implementation, and highly scalable. So you can write cross-platform code with the same declarative description, but different implementations. So you're already writing declarative code in a sense, because Objective-C is a step forward from C on the declarative spectrum. C is all about manual memory management and dealing with structs and pointers, blah, blah, blah. Objective-C, you still have pointers and structs, but then you have objects, which are they're these abstract entities which have properties, and you can message them, you can ask them to do things. It's a step above C. And C++ also has classes, so there's that. And then there's Swift, which offers more declarative features than Objective-C. Then there's Metal and OpenGL, and there's Core Graphics and SceneKit. So how many of you have used SceneKit here? Yeah, so you already know how easy it is compared to doing the raw GPU processing on your own. And Core Graphics is also based on Metal and OpenGL. So you don't have to manipulate the raw pixel buffers yourself. You get it all in a nice wrapped abstract way procedure. Okay, so imperative versus declarative. This is similar to what I showed you earlier, but this it's a better example. So these are two ways of, we start out with an array of numbers, and we want to filter out the all the multiples of 3. So we can do it the imperative way, which is looping with a for and loop, or we could do it the declarative way, which here I declare an extension to int, and I use filter instead of the for and loop. So the second block reads better than the first block because it's immediately apparent what you're exactly doing, because I'm filtering, and then I'm filtering by testing whether it's a multiple of 3. In the first one, I'm using the modular operator. That's great. I mean, most of you know that it's the modular operator and what it does. But then it takes a little more time to understand than the declarative version. It's the same thing. So yeah, so we declared an extension, named our function based on what it does, replaced the for and loop with filter, and wrote flatter and more readable code. So flatter code is also important when you're writing declarative code. Flatter is better for the brain. We process things linearly, not non-linearly. So it's easier to process, yeah. So yeah, avoid for and while loops. Of course, you can't avoid them entirely, and you shouldn't when they're absolutely necessary, but whenever you can, you should replace them with reduce, map, filter, etc. And if you can't replace them with reduce, map, or filter, then you should write your own higher order function. So for example, the standard library has this structure called repeat, which takes an element and an integer, and it basically gives you a sequence that repeats that element for the number of times you specify. You could do that with a while loop, but the standard library just provides it as a struct, and you can use it in a flatter format. So it's more declarative than using a while loop. Okay, so there's strong declarative programming, and then there's weak declarative programming. Strong declarative or pure declarative programming is when you only tell the compiler what to do, but not how. And weak is when you tell the compiler what to do, but also how. And there's a layer of indirection between the declarative and imperative part of the code. So language primitives. Basically, the pure declarative languages, they offer language. The units of the language themselves are what you use to describe the program. You don't have to do anything beyond that. Like you use the fundamental units, and there's usually only one way to express your program in a declarative language. So yeah, provide language primitives that describe the what aspect. In computing, language primitives are the simplest elements available in a programming language. Yeah, Swift is not pure because you can write the same program in multiple ways. It doesn't prevent you from writing imperative code or mixing imperative or declarative code. So this is a good definition, good property I found online. So The declarative property is where there can exist only one possible set of statements that can express each specific modular semantic. Basically, this is what I was saying earlier, that you can only express your solution in one way. The language doesn't allow you to express it in another way. So there's no ambiguity as to what is the better approach. There's only one way to express it. So pure declarative languages expose this, and a way to emulate this is to write a DSL. Okay, so DSL stands for domain-specific language, which I'm sure most of you are already familiar with. So examples of DSLs, SQL, which everyone, I guess, should be knowing, HTML, XML, and VFL. How many of you know what VFL is? Yeah. So visual format language. It's a language that lets you create multiple constraints at once using a very compact expression. This is for auto layout. Yeah, the two properties we're interested in is that it's declarative and that it's stringly typed. And stringly typed is bad, error prone, and it's dynamic, which is unnecessary because in a language as static as Swift, you're losing out on the static checking. So this is Apple's documentation. It's a picture from the documentation. So the top part, you're separating a button and a text field with a standard spacing. Now, what I'm doing here is I am declaring and I'm overloading the subtraction infix operator to replicate this, the visual format language, the text there. But I'm replicating it as a DSL in Swift. So what I do is, first of all, I extend collection of 1 to support array literals, so that I can, get a collection of a view, and then I overload the infix operator, the subtraction operator, to get the same visual look of the visual format language there, and then I create the constraint, and it works. It just works without the stringly typed interface. So yeah, we basically did this. We turned something that was stringly typed and we wrapped it in a static and a type-safe manner. Yeah. So declarative Swift has a one-to-one correspondence with the developer's mental model. Does not change if the underlying implementation changes. Expresses code logic via natural terminology. Extensively uses protocols to describe the what aspect. Extensively uses protocols as definitional elements and prefers generality over specificity. And it makes use of Swift's strongly typed nature by pushing semantics into type names. This is an example of how you could write a declarative UI framework. I've been dabbling with this. So the basic concept is you have iOS and macOS, they use UI view and NS view. Now, how do you wrap it in one declarative format? So you create a structure for color, which represents, which creates a UI color reference. The color is just RGBA values. And then you have a structure for view. This is a very simplified and minimized version of it, of what a view can be, but for the purpose of this talk, I'm just going to use this. So there's the frame, the background color, and it generates a UI view. Similarly for macOS color and view, but instead of UI color and UI view, we're generating NS color and NS view. Now you can combine the two using if-defs, and you can create a single wrapper for both platforms, so that you can have cross-platform UI with a declarative with a declarative syntax, and without needing to write separate implementation, without needing to write separate code for both platforms. You are writing separate code, but it's hidden by the view abstraction. Okay, so yeah, we abstracted over AppKit and UIKit, expressed UI view, UI color, NS view, and NS color as codable structs. So there, you can serialize them and added a layer when direction, yeah, scaled across iOS and macOS with one declarative description. Okay, pushing semantics into types. Basically, the idea is that because Swift allows you to, Swift encourages that you create your own custom structures and types, and there's no runtime penalty. So you should make full use of this feature, and you should use strongly typed code wherever possible. So let's take an abstract file system operation, which takes file path, as a string. It checks whether the path is absolute. It does something if the path is absolute. If it's not absolute, it throws an error. Now, how can we improve this? How can we make this more declarative? So we declare two structs, one for any type of path and one for an absolute path. And the absolute path, it validates whether the path is absolute or not at the initializer itself. So what we can do now is we can simply write this. This eliminates the throwing mechanism. You don't need to worry about errors. And it makes it clear that you're using an absolute path in the function. So you don't need to document that, I'm using an absolute path. It's already there in the type name. And it prevents deferral in favor of validating and initialization. What this means is that you don't have to worry about errors when you're performing the operation. You just have to worry about errors when you're initializing the path, the first time you're stating that it's an absolute path. Okay, think generic. Generics encourage declarative thinking. They force appreciation of the what instead of the how, because you're working in generic context. You don't know the concrete type. They increase modularity, scalability, and reduce boilerplate. Protocols. You use protocols to describe the what aspect. They tie in strongly with generics. You use it to create definitional networks, and you push documentation into protocol names. So self-documented code, like pushing information into type names. It's the same idea. Swift protocols aren't Objective-C protocols, and they're often cost-free at compile time, as in they don't have the same runtime penalty. So don't hesitate to make one, and yeah, just feel free. So suppose I have an init, and this is something almost a lot of types have, and it's a very common function. So Swift doesn't have an initiable protocol in the standard library, which I think they should, but you can create one, and don't wait for the generic scope to come to you. You should use protocols to make it clear that a certain aspect of your code is being repeated across your code base, and the moment you create a protocol with a good name, then it already expresses what the function does, or what the type can do. So you don't need to document that. You can initialize it with init because it's already conformant to initiable. Okay, so this is an example of how you can use protocols to write generic data structures. This is a generic protocol for a graph and a graph edge. An edge connects two vertices, and a graph is basically a set of vertices and a set of edges. And then this is a directed edge, an edge that starts from one end and ends at starts from one vertex and ends at another vertex. The direction is clear. So we're all using, we're just using protocols. We're not using any concrete types, no structures, we're using sequence instead of array, because this allows us to scale for custom sequences or whatever you want. So assume nothing. We define the concept of a graph and edge via protocols. We use associated types for the sequences of the edges and vertices instead of what we typically use, array or derived a protocol for the directed edge from the graph edge protocol. Those are two separate things. So and they one inherits from the other. So it's very clear. And then we assume nothing. So vertices and edges can be any sequence type: a set, an array, a contiguous array, a linked list, or any custom sequence or container. this is what I use to describe a matrix, and it's very big, and it might seem a little intimidating, but the point is that I am not assuming anything. I'm not assuming what the index of the what indexes the rows, what indexes the columns, because I could be working with a really large matrix type, and if I just used int to describe an index, then I just limit myself to the maximum bound of int. And collection, the protocol, it defines functions that allow you to move the index. So like collection, my matrix protocol, it has functions that allows you to move a row index or a column index. So all the moving of the indices is delegated to the collection type itself. So think big. I mean, always think about the most general description about something. Here, we are not assuming anything. We're not assuming what the count type is. We're not assuming what the index type is. We're not assuming what the row or column index types are. And we're thinking in completely generic terms. So, and always blueprint as many functions as you can. Blueprinting is just defining the function in the protocol so that so that a type can. So you'd mostly implement a lot of the functions in the previous the what, not the how. You should replace imperative constructs with declarative ones. You should push information into types so that your code is self-documenting. You should push information into protocols, like I did with the graph and the matrix protocols. And you should write generic code. And the conclusion is that declarative programming is a way of thinking. It's not an API. It's not a framework you import. It's not some GitHub project. It focuses on the separation of concerns, especially in impure declarative languages, because you have to write imperative code and declarative code. So you can't just write declarative code, so you need to separate those two things. Generic contexts force you to appreciate declarative programming, because they force you to think in terms of the what instead of the how. You're not given the implementation details. You're working with, And Swift is great for declarative programming because it has all these features. So that's it. Thank you.